You clicked because someone told you that Mythos can train your code 52 times faster than human effort, but the real stakes are far higher than just speed numbers. If you believe this claim without understanding the underlying architecture, you risk wasting thousands of dollars on hardware configurations where your expensive GPUs sit idle while waiting for data to arrive from memory. By watching this video, I will show you why that 52 times figure is not a magic bullet but a fragile outcome dependent on how well you align your deployment strategy with physical memory constraints rather than just chasing theoretical throughput. Let us start by looking at the hardware reality facing every engineer today. For years, we have operated under the assumption that adding more compute power would linearly solve our problems, yet the landscape has shifted dramatically due to a widening disparity between processing capabilities and data movement speeds. While server floating point operations per second scale at 3 times every 2 years, dynamic random access memory bandwidth only scales at 1.6 times in that same window, and interconnects lag even further behind at just 1.4 times. This creates what researchers call the memory wall, a fundamental bottleneck where your accelerators simply cannot get fed fast enough to perform calculations, rendering raw compute power irrelevant without architectural changes. Consider how this impacts modern large language model training workflows, which demand exponential growth in capacity that outpaces physical hardware limits by hundreds of % annually. In fact, LLM training needs grow 750 times faster than memory capacity can be expanded, creating a scenario where engineers face a critical trade-off between optimizing for CPU-bound orchestration and achieving GPU saturation. When you push systems to maximum theoretical throughput without addressing data movement, you often end up in costly misconfigurations where your accelerators sit idle waiting on data transfers, rather than performing the calculations they were designed to execute efficiently. This is why automated tools like Microsoft's Model Builder can sometimes exacerbate the problem by selecting oversized architectures such as ResNet that underutilize available GPUs and trigger redundant computations, effectively creating artificial bottlenecks despite having powerful hardware sitting right in front of you. You might see high accuracy results from these models on paper, but when you actually attempt to train them with inefficient frameworks or software orchestration layers, the system cannot hide latency, leading to hours-long waits even with consumer-grade cards like the RTX 2080, simply because CPU-bound data loading becomes the new limiting factor. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Here is where most people get confused by the 52 times speedup claim and why it feels so contradictory to their daily experience of slow training times. The reality is that this massive improvement likely masks a fundamental architectural shift from compute-bound execution to memory bandwidth-limited operation, meaning the CPU orchestration overhead becomes the new bottleneck once you achieve full GPU or TPU saturation. When you optimize for one side of this equation without understanding the other, you end up with transient velocity spikes in your development workflow that introduce long-term slowdowns through accumulated technical debt and quality degradation, complicating any narrative about immediate speed gains from AI coding assistance. Think of it like trying to fill a swimming pool with a teaspoon while the drain is open. No matter how much water you pour in, if the hole at the bottom is too large, you will never reach your goal regardless of how fast you can scoop. In our case, the pouring speed corresponds to raw compute power, which has exploded recently. But the drain represents memory bandwidth and data movement, which simply cannot keep up with the growing appetite of modern artificial intelligence models. When engineers assume that adding more GPUs or faster processors will solve everything, they are essentially trying to pour water faster into a pool with an unmanageable leak, leading to diminishing returns once the system hits its physical limits. The evidence suggests that specific training workflows can still suffer from inefficient model selection or software orchestration layers independent of hardware limits, which means we cannot dismiss performance issues solely as memory problems, but must recognize where CPU-bound overhead creates artificial friction in our pipelines. Real-world adoption shows us that when high-accuracy models are trained on architectures unable to hide latency, the result is a system that looks powerful on paper but performs poorly under load due to insufficient bandwidth relative to model size. This disconnect between theoretical peak performance and actual runtime behavior is where many projects stall or fail entirely because teams focus on the wrong optimization targets. Now consider what happens when you try to scale this approach across multiple machines in a distributed environment, as interconnect speeds lag even further behind memory improvements, creating new points of failure for data synchronization. Your network becomes another drain in our swimming pool analogy, where packets must travel between nodes before any meaningful computation can occur, turning what should be parallel processing into serial waiting games that negate the benefits of adding more hardware to your cluster. This is why simply buying faster servers or upgrading GPUs often fails to deliver expected results unless you have rethought how data flows through every layer of your stack, from storage to memory to compute units. The 52 times speedup claim must therefore be reframed not as an inherent property of new chips, but as a fragile outcome dependent on aligning deployment strategies with physical memory constraints rather than just maximizing theoretical throughput across the board. Engineers who understand this trade-off can design systems that prioritize data locality and minimize unnecessary transfers, whereas those who chase raw numbers will find themselves stuck in loops of expensive hardware upgrades that yield little practical improvement over time. It is a delicate balance between CPU orchestration efficiency and GPU saturation, where one misstep leads to wasted resources and another brings the speedup you are looking for without breaking your budget or timeline. Understanding this dynamic changes everything about how we approach performance engineering today, moving us away from blind faith in hardware specifications toward a more nuanced view of system architecture that respects physical limitations while maximizing available throughput through intelligent design choices. The path forward requires acknowledging that memory bandwidth is now the primary bottleneck and designing around it rather than trying to force compute power where data movement cannot keep pace with demand. This shift in perspective allows us to build systems that are not only faster but also more reliable and cost-effective, ensuring that every dollar spent on infrastructure translates into actual productive time for your development teams. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.